Okay, hello. This is a description of the Boruvka algorithm. We're going to go into background history, how the algorithm works with a couple of examples, and an implementation within Python. So, the Boruvka algorithm could be said to be the first graph-solving algorithm. It was developed in 1926 by Czech mathematician Oktay Boruvka, and it was initially used to help solve the West Moravian power problem by finding a minimal spanning tree with the power cables. Let's explain this a bit further. So imagine this is a power station, and these are subsequent wires. If a wire was to lead to each home, this would incur high costs because you would have there'll be a lot of weighted wires because there are more efficient ways to arrange the wires so that lower costs are incurred. So let's look into this. So if we were to connect houses in this format, where one house connects to another house, and find the lowest path between all of them, that would incur the lowest cost, and that is what the Boruvka algorithm looks to solve. This is also, in simplest form, a description of a minimal spanning tree. We will explain this in a second. So, the Boruvka algorithm helps determine the minimum spanning tree of a given weighted inputs. A spanning tree is a subgraph that connects all vertices present in the input graph. Although, what makes a minimal spanning tree different from a normal spanning tree is that a minimal spanning tree is a tree where the weights are kept as low as possible. Additionally, in MST, a minimal spanning tree cannot have any cycles and it cannot have any loops. You understand? So you cannot repeat over any nodes. Examples of some spanning trees and minimal spanning trees are below. So given this input graph, these two would be spanning trees as they connect to every node. For example, boop, boop, boop. While this is a minimal spanning tree, as it connects to every node and the weights are kept the lowest. This is the MST at the end, eighth, after adding all of them. So this would be a bad minimal spanning tree because of the cyclic nature, as this goes to this goes back here, and this. This cyclic nature cannot occur in minimal spanning trees. Okay, let's continue. The Boruvka algorithm is also a greedy algorithm. This means that during each step of evaluation, the most optimal solution is taken. So given a tree of tasks that need to be completed, in the example of a greedy algorithm, it would the algorithm would pick the lower cost here, then follow that up with the lowest cost here, and get an evaluation cost of 12, when that is not the most optimal solution, as if you go take the higher cost on the first one, but then take a lower cost, overall you may take the lowest evaluation cost. So why use a greedy algorithm? A greedy algorithm is still a very good estimation of the most optimal solution. So let's describe how the Boruvka algorithm works essentially. So given this as our input graph, let's use the Boruvka algorithm to find the minimal spanning tree. Okay, a second. So what the first step of what the algorithm looks to do is add of the lowest cost of every node into the minimal spanning tree. So it evaluates the lowest cost for each node and then adds that to the minimal spanning tree. So let's use this tree as an example and use this highlighter to highlight the paths that are chosen. So initially, A will be evaluated and it has two neighbors, essentially B and C. As we can see, it will compare 8 is greater than 7, so the path 7 is chosen and added to the minimal spanning tree. Then B is evaluated. After A, B would be evaluated, and the lowest cost would be 8. As you can see, the rest are 10 and 15. The lowest cost would be 8, so that is also added to the minimal spanning tree. So C is then evaluated, and the lowest cost from C, which would be 7, but as it's already connected to A, that is just confirmed in, and that can be moved on. Okay, next we evaluate D. The lowest cost of D would be E, and that would be the first iteration. We would evaluate at E, and we would see that the lowest cost for E would also be D. So, this is the lowest. How do I say it? The lowest cost for the first iteration. On the second iteration, let's see what happens. Let's use a different color to evaluate. So, although on the second iteration, all connecting nodes are put into the set as a single unit, so we would have A, B, and C. So we were trying to find the lowest cost from out of any of these to any part of the graph that is not connected to this graph. To the set. So the lowest cost from A, B, and C would be this 10, as the others are 11 and 15. We couldn't choose this 10 because that would make the graph cyclic, which is not allowed. Neither would we need to highlight this 7, as that is already part of the set. It's already part of the set, so it wouldn't make sense to include it. So we would go into the DE evaluation, and we'll see that the DE evaluation would be the exact same 10 that we just evaluated. It would be, again, this path, confirming that our minimal spanning tree comes down to be, in essence, looking like this. So this is the general idea of what a minimal spanning tree is, and how we can use the Boruvka algorithm to find a minimal spanning tree given a weighted graph. Thank you for watching.
Hello, this is my implementation of the Boruvka algorithm in Python. This is the main function, which houses the Boruvka algorithm. As input, it takes in a 2D array. Each inner array, for example, 0, 1, 8, corresponds to a connection between two nodes. Let's look into this a bit deeper. In the first index, we have 0, which represents the first node being 0. The second index, we have 1, which represents 1 being the second node. And we have 8, which is the cost of the path between the two nodes. Subsequently, we have a node 0 connected to the node 2 with a weight of 5. We have 1 connected to the node 2 with a weight of 8, and so on and so forth. When ran, the input graph is then showed to the user. As we can see, all connections present here are displayed here accurately. Then, when X is pressed, the minimal spanning tree is produced. The minimal spanning, as we can see, this is an accurate minimal spanning tree, as it has all nodes in the input graph are present in the minimal spanning tree. There are no jumps, all breaks within, so all nodes are connected. And lastly, there are no cycles or loops in this tree. This implementation also works with harder, more complex graphs. For example, if we put in the graph we put in this graph, which looks way more complex than the previous, we still get an accurate minimal spanning tree. Thank you for watching.